welcome to everybody and to this September seminar. So my name is Peter Taylor. I'm a Professor of Sustainable Energy Systems at the University of Leeds and one of the co-investigators of the EPSRC funded Network Plus on decarbonisation of heating and cooling. And this event is organised through the network and is part of a series looking at the different challenges of decarbonising our heating and cooling sectors. This month, we're delighted to welcome speakers from Northumbria and Oxford universities who have led projects funded by the network, researching the deployment of domestic heat pumps and the use of green hydrogen for building decarbonisation. So with that, I think we should move to our first presentation. So I would like to introduce our first speaker, who's Dr. Lu Xing. She's an associate professor in the Department of Mechanical and Construction Engineering at Northumbria University. So Lu obtained a master's and Ph.D. degree in Mechanical and Aerospace Engineering from Oklahoma State University, where she participated in multiple research projects in renewable energy technology and software development. Prior to joining Northumbria in 2020, she was appointed as an assistant professor at the China EU Institute for Clean and Renewable Energy at Huazhong University of Science and Technology, where she led several projects on decarbonisation in buildings, transport, and on hydrogen and fuel cells. And so with that, I would like to welcome Lu, and please give us your presentation.
Thank you everyone for coming today. I'm Dr. Lu Xing from the Northumbria University. My research field is in decarbonization in the building and transport, smart grid, hydrogen and fuel cell. So today I will present the 6 months network funded project, Distributed Green Hydrogen for Building Heating and Cooling Decarbonization, completed by my team members, Han Hui, Chris, Joe, Samit, and Prasad from Northumbria University and Durham University. Based on the completed work, we have submitted for 1 journal paper, and we are in the process of submitting another one very soon. Me and my team members appreciate the support of the network and Engineering and Physical Science Research Council of the UK for the sponsorship and completion of this project. Thank you. So to understand how we decarbonize for the building heating and cooling, first we need to explore the past. So where are the greenhouse gas emissions coming from? A recent publication on the open access journal, which is Frontier in the Sustainable Cities, found out about more than half of the greenhouse gas emissions is emitted by 25 megacities from the studied 160 global located cities. If we look at the figure on the left, which shows that the global greenhouse gas emission by sector. So we can see that the energy takes about 73.2% of the whole total emissions. And on the right side, we can see that the building heating and power takes about 17.5% of the whole gas emissions. So the question is, why we need hydrogen? Hydrogen has the highest energy content by weight of any chemical fuel, 3 times higher than gasoline. It is critical feedstock for the chemical industry, including the oil refining and fertilizer production. It also powers the fuel cell with 0 emissions. As we can see, hydrogen is linked in the figure on the left. Hydrogen has been linked with power generation, synthetic fuel, hydrogen vehicles, ammonia, fertilizer, metal refining, and heating. So the right side of the figure also shows that the hydrogen as an energy storage method can be integrated into the smart grid for maximize the usage of the renewable energy for city buildings and factories. So when we mention hydrogen for decarbonization, especially the decarbonization for building, heating, and cooling, actually there are different types of hydrogen. Currently, more than 90% of the hydrogen is produced from the fossil fuel by steam reforming of natural gas, coal gasification. Based on the carbon emission, we can have the gray hydrogen, the blue hydrogen, and green hydrogen. So the green hydrogen production is powered by renewable energy sources like solar power or wind power through the water electrolysis to split the water into hydrogen and oxygen. There are different types of electrolyzers, as you can see in the figure on the right side. In this research project, we investigate the PEM electrolyzer, which has its ability to operate at high current densities. This can result in reduced operational cost, especially for systems coupled with very dynamic energy resources like wind and solar. So we can see actually on the right side, the PEM electrolysis cell, that how the cell can use the power, solar power, to split the water into hydrogen and oxygen. And then also we have in the figure, which is the PEM fuel cell, which is able to utilize the hydrogen and oxygen as input, transform the chemical energy liberated during the electrochemical reaction to electrical energy. And we can use that in electric energy for building applications. So the PEM fuel cell are commonly used in the stationary power applications due to high power density, low operating temperature, and low emissions. So we just introduced some background of the research. Now we discuss motivation of this research project. In UK and European countries, electrification of heating and cooling provisions where heat pump, electric heater, or electric boiler provide a pathway for carbon emission reduction. Therefore, we propose developing a building distributed multi-energy system integrated with hydrogen to decarbonize the electricity generation for the building, heating, cooling, and lighting. Specifically, we want to explore mainly two aspects in this research project. First is hydrogen as an energy storage method for decarbonization in the building sector. Second one is the application of the concept of circular economy. To decarbonize, the green hydrogen seems to be a promising solution. While in this process, there will be a large amount of water usage, wasted energy, and material. With the proposed system, which has an integration of the PEM electrolyzer and fuel cell, the water used by the PEM electrolyzer can be circulated to the PEM fuel cell to ensure the water, hydrogen, oxygen recirculation in the system. Originally, we want to explore both the energy and material circulation because in the system, we have a large amount of heat generated by the operation of the electrolyzer and fuel cell. However, due to the constraint of the time, because this is only a 6-month project, so finally with the team, we decide to continue those as team's future collaborative work. So as shown in the figure 1 on the right side, is the graphical representation of the proposed system. In this system, the PV panel is integrated with the PEM electrolyzer and fuel cell to provide building heating, cooling, and electricity. Hydrogen is used as an energy storage method in this system. So we can imagine, typically we have the PV with the battery storage to provide the building electric load. Now the battery has been replaced by PEM electrolyzer and PEM fuel cell. So compared to the battery energy storage, which is a short-term energy storage for hours, hydrogen energy storage can make it possible to compensate for longer-term fluctuation, even though higher losses occur due to lower efficiency. To our knowledge, this research is the first kind of analysis related to the modeling and investigation of both hydrogen electrolyzer and fuel cell integration into the distributed multi-energy system for the building application. In the previous or existing research work, we already see there are projects investigating the hydrogen fuel cell for meeting building energy demands. However, in this project, we are proposing the integration of the electrolyzer and fuel cell for the building application. So the question is, when we only have the fuel cell for the building application for providing the building energy demands, we have to wonder, where are those hydrogens coming from? So are they blue hydrogen, gray hydrogen, or green hydrogen? If they are gray hydrogen or blue hydrogen, then we have to really be careful about whether we really decarbonize through the hydrogen application. So if we have green hydrogen produced and used with the fuel cell, how much energy losses will be through the transport of the hydrogen to the building site? And the third question would be, what about the water footprint? which is a question which hasn't been paid much attention, or maybe some research, very few, has started to pay attention to, is during the process of the electrolysis, a large amount of water will be consumed for the green hydrogen production. So to answer those questions, that's why we proposed the research in this project. So by proposing an integration of the PEM electrolyzer and fuel cell into the building energy system, that there are several benefits we can possibly gain from the proposed system. The green hydrogen is produced and consumed locally at the building sites. So this will eliminate high cost and energy requirement for the hydrogen transportation. And also, this system suggests possibility for energy autonomy, essentially due to the end, which is a very essential concern we have to pay attention to due to the current energy, climate, or war crisis. And then the distributed system can be connected to the smart grid, which enable the real-time energy and carbon trading and system optimization. Finally, putting the PEM electrolyzer and fuel cell together. So the fuel cell would generate water, which can be consumed by the electrolyzer. So in that way, the footprint of the electrolytic hydrogen will be considered to ensure the viability and sustainability of the hydrogen production. So by investigating those aspects, this study aims to provide valuable insights into the potential of hydrogen integration in building application and inform decision-making process for a sustainable energy transition. So the research objectives are as follows. This research aims to comprehend interaction mechanism between the PV module, the water electrolyzer, and fuel cell. Comprehensive assessment from a holistic, technical, economic, and environmental integrated perspective is investigated for evaluating the system's feasibility. So we mainly have two objectives, which are developing model for the hydrogen integrated building distributed multi-energy system that produce and consume hydrogen locally at the building sites, simulate and analyze the dynamic system response, and evaluate system performance characteristic for the building application. So the whole system is with the electrolyzer powered by the solar cell, and the fuel cell generate power with the hydrogen produced. Design and simulation of the proposed system for investigating the green hydrogen into the building application. So we aim to achieve a cycle of the water, oxygen, and hydrogen in an electrolytic cell and fuel cell system under the following assumptions. So we assume that the supply of the water is unlimited. The cooling system is sufficient to maintain the fuel cell and electrolyzer as required condition. No additional loss of the water, oxygen, or hydrogen during the transport process. So here in this slides, the figure 2 presents the schematic diagram of the proposed system. So in this figure, we have a solar PV, electrolyzer, fuel cell. So this is the electrolyzer, fuel cell, solar PV, and the building loads is used as the input. And also we have a cooling system to maintain the system condition. So we start from here, which is the existing water coming out of the fuel cell stack at a temperature of 80 degrees Celsius. Going through the cooling system will be cooled down to 20 degrees Celsius, and this will be pumped through, goes through the ion exchange resin cartridge to deionize the water and then enter the stack of the electrolyzer. So on the other hand, the solar panel will provide the power for this electrolysis process. So the existing on the anode side is the water and oxygen. The water will be recycled, and after it passes through the anodic water gas separator. So the oxygen will go through a drying and purification process, and later will enter the cathodic water gas separator and another humidifier before it enters the fuel cell stack. On the other hand, the hydrogen coming out of the electrolyzer stack will go through a cathodic water gas separator and go through a drying process, and finally will recirculate as an input to the fuel stack. With the oxygen, the fuel cell will convert those energy into the power supply to meet the building energy demands. So the current system operating strategy is, so for example, for the residential building, we have a case study on. There's a hydrogen tank of 3 to 4 kilograms of hydrogen at first. Any solar PV power will be converted to the hydrogen through the electrolysis process. And later, whenever the building energy requires, then the fuel cell will convert the stored hydrogen into the electricity whenever needed. So this page presents more details of the PEM electrolyzer and fuel cell. As shown in this figure 3, what we have explained before about the water electrolyzer and the fuel cell. We are connecting both of them together. And in the table 1 here is a parameter for electrolyzer and fuel cell, which shows that what we have selected for the simulation purpose. So the data for the solar irradiance and the solar PV model that is actually presented more details in the report. We select the data from the London data store for several sites, 20 substations. The simulations were performed to analyze the seasonal variation. And the parameters of the solar panel has been summarized in the table 2. 350 watts for the average is selected as average power based on the data we get for the commercialized solar panel power output. So the methodology part, another important input to the model will be the building energy demands. So the buildings are designed as SketchUp and then in the Open Studio plugin with the Energy Plus software. So the residential house is drawn as shown in the figure 4. We developed building models for 2-story residential house. We developed models for office building and apartment to see different types of building, how that affects the system design and feasibility study results. We also performed sensitivity study and verified the building loads for different types of buildings. So the case study for the residential building, that we have about 150 square meter roof area, total floor area 450 square meter. We kept the room condition at 18 degrees Celsius in heating and 23 degrees Celsius in cooling. Figure 5 and 6 represent the building heating, cooling, and electricity demands for the summer and winter days, respectively, for the residential house in Aberdeen, UK, for summer and winter day. So figure 5 shows that the hourly electrical consumption during a summer day, which is the July 1st, which we selected for the house model. And we can see that the highest consumption is observed at about the x-axis is the hours of the day, and the y-axis is the energy demand. So we can see that the highest consumption occurs at around 6 p.m. with a value of 2.2 kilowatts hour. There's no cooling or heating requirement for the house located Aberdeen during that day. Figure 6 shows the electrical consumption of the winter day, which is December 12th of the house model. So the highest consumption is observed at 8 p.m. with a value of 11.4 kilowatts hour. The total consumption requirement is highest during the night. So it's quite obvious that the winter day that the electricity consumption is much higher. The total electricity consumption during a summer day is only about 30% of the total electricity consumption during a winter day. So this is the hydrogen integrated building distributed multi-energy system simulation results for the summer day we have selected. July 1st is a selected date for the case study. So figure 7 shows the solar irradiance, the solar power which we can collect from the PV panel on the day based on the measured solar irradiance data. And figure 8 present electrolyzers, the water consumption, hydrogen and oxygen. Their ratio is about 1/0.11 and 0.89. Figure 9 presents the PEM fuel cells, water generation, hydrogen and oxygen consumption. So during this summer day, the fuel cell consume hydrogen at about 0.02 grams per second at peak consumption. But the maximum hydrogen production is about 0.15 grams per second for exceeding the maximum consumption. And in fact, happens before the peak consumption occurs at 7 p.m. So this is the results showing for the winter day. Figure 10 is also the solar irradiation. And then the 11 is the electrolyzers, water consumption and hydrogen and oxygen generation. So what we observe here is that for example, in figure 11, that the maximum water consumption in figure 11 is about 0.9 grams per, because the x-axis is the time of the day and the y-axis is the flow rate. So we can see that the maximum water consumption is about 0.9 grams per second around 1 p.m., which is lower than in the summer day case, which we present in the previous case. Is about 1.5 grams per second. The reason for that is because the electrolyzer, that the hydrogen production is highly correlated to the solar power we can collect. So that's why in the winter day, we have less hydrogen produced and less the water consumption. The trend in the figure 12, the trend in the water production mirrors the variation in the electricity consumption in the residential building. So the conclusions we have for the case study, this study presents a proton exchange membrane, water electrolyzer, and fuel cell system powered by renewable energy to meet the building energy demands, achieve electricity decarbonization and energy autonomy. The water recirculation of the system has been considered. The case study results for the residential building in Aberdeen, UK has been presented. The analysis results shows that on the summer day, July 1st at 7 p.m., when the daily energy demands is at peak, 11 solar panels are required to meet maximum daily building energy demands and ensure 100% of the water recirculation. On the winter day, December 6th at 1 p.m., even all 75 solar panels can be operated simultaneously. System can only meet 26% of the total building energy demands. So these findings provide valuable insights into the potential implementation of electrolyzer and PEM fuel cell in the real-life application. However, we are aware of the limitation of the work. Because it's only the simulation for one day, we didn't really consider the seasonal changes. Therefore, we have also performed some extended work for assess the system feasibility for the office over a year period of time. So we have choose 18 locations, a variety of different climates. As you can see that some humid, continental, mild climates or hot summer climates in UK. And our model results shows the office block simulation across the UK location with a range of 100 to 110 kilowatts hour per square meter per year. And then we have also verified that against the UK government published report to verify the estimation results. So this figure shows that the office block over the year time, the energy consumption, and also in 2 typical days, what are the energy consumptions. So this is the results we get so far for the extended work for the office building. We are still in the process of processing the data. For example, figure 8.5 is the water and hydrogen consumption production within 8 days. And then also we show this water and hydrogen production balance. On the right side, is the figure shows that figure 8.6 shows that the water and hydrogen consumption production within 1 year. So what's obvious is we see the water consumption, which is really correlated with the solar PV, solar power we can collect through the year. And then when we see water production, which is produced by the fuel cell, which is highly correlated to the energy demands as we need it. So far, the conclusions for the extended work is that using the proposed PEM electrolyzer and fuel cell integrated system for building application, about 71.8% of the energy demands can be met without considering the storage limitation. Energy conversion efficiency of the whole system is about 80%. So the production of the hydrogen rises in summer when the building energy demands is relatively low. So there's a peak hydrogen surplus calculated to be approximately 1,128.3 kilograms. So finally, for the future work, we are suggesting to further validate the model accuracy, we need infrastructure development to ensure the successful establishment of such a project in practice. And another suggestion is the improved operational strategy can be investigated. That's because currently we directly store the energy into the hydrogen form. But ideally, would be whenever the solar PV panel, we can use it to power the office building directly, that would be the perfect. But if at that moment, the building energy is not needed, there's no requirement, so we can store that in the form of hydrogen. So hydrogen can be used as a supply of energy storage and of emergency usage. So this is the end of my presentation, and thank you for listening.
Thanks very much, Lou.